music. RNNs are making these dreams a reality. Traditional neural networks are like amnesiacs. They treat each input as an isolated piece of information, with no memory of what came before. Imagine trying to understand a sentence by looking at each word in isolation, without any context. It would be nearly impossible. RNNs, on the other hand, have a remarkable ability to remember. They process information sequentially, maintaining a hidden state that acts as a memory bank. This hidden state is constantly updated as new input is fed into the network. Previous inputs influence the processing of subsequent ones. Think of it like reading a book. Each word you read adds to your understanding of the story. Your memory of previous words and sentences shapes your interpretation of the current one. RNNs work in a similar way, allowing them to capture the nuances and complexities of sequential data. The real magic of RNNs lies in their wide range of applications. They are powering breakthroughs in fields like natural language processing, speech recognition, and time series analysis. Let's explore some real-world examples. Speech recognition software like Apple's Siri or Amazon's Alexa relies heavily on RNNs. These networks can analyze the sequence of sounds in human speech and convert them into text. This complex task is made possible by the RNN's ability to remember past sounds and use them to predict the next word in a sentence. Another fascinating application is language translation. RNNs can learn the grammatical rules and patterns of different languages, allowing them to translate text from one language to another with remarkable accuracy. Services like Google Translate are now powered by RNNs, breaking down language barriers and connecting people across the globe. RNNs also excel at time series prediction, where the goal is to forecast future values based on historical data. They are used in finance to predict stock prices, in meteorology to forecast weather patterns, and even in healthcare to predict patient outcomes. While RNNs possess the remarkable ability to remember, their memory is not without its limitations. One of the main challenges in RNN training is dealing with long-term dependencies. This occurs when the gap between relevant information and the point where it is needed becomes too large. Imagine trying to remember a specific detail from the beginning of a long book. As you read further, your memory of earlier details may fade. RNNs face a similar problem. The influence of past information can diminish over time, making it difficult for the network to capture long-range dependencies. This phenomenon, known as the vanishing gradient problem, can hinder the performance of RNNs, especially in tasks that require remembering information over long sequences. Fortunately, researchers have developed advanced RNN architectures to address this challenge.